Hello and welcome to Lost in Science. We are going back through our archives again this week. Claire is going to fill us in on a conservation project involving the 40-spotted pardalote, an endangered bird in Tasmania. I will be revisiting our story on hot black ionic ice, and Chris will be taking us through the physics behind the tears of wine. Please stay tuned.
Do you know how much I love a conservation story? Well, let me tell you, this one has it all. Rare and difficult birds, check. Parasitic worms, check. Human invention, check. And of course, like any good story, chicken feathers, check.
Can you fit in some crafting as well, Claire?
Oh my goodness, there is so much crafting in this. How did you know?
I think I might have heard this story, yeah.
Okay, great. Well, strap yourselves in, even though you might have heard it, because it is a rollicking good tale. It is the story of the 40-spotted pardalote. So let's start at the start. The 40-spotted pardalote is an extremely rare Tasmanian songbird. So it's about the size of a ping pong ball. It has lovely green feathers, very olive green, and a smattering of, you guessed it, spots on its wings.
Would there be 40 spots?
I assume. Now, when I say rare, I mean so rare it is about to go extinct, caused mostly by deforestation across much of mainland Tasmania, and it now survives in pockets mostly on islands off the east coast of Tassie. So think your Bruny Islands and your Maria Islands, and it's in very small numbers. What is also very remarkable about the 40-spotted pardalote is that they forage mostly in the foliage of white gums, and what they eat there is something called manna, or mana, which is a sweet and crystallized form of tree sap. Now, I'm told that many Australian birds feed on manna, but these little birds are unique because they sort of farm it. So they use their beaks to put these tiny little nicks in leaves and stems, and through these little nicks the white gum actually stimulates more of this manna production. So they're not only sort of eating it, but they're also stimulating the plant to produce more of it.
That's pretty smart.
Very smart, very smart. Okay, so obviously you are inevitably charmed by our protagonist bird. So now I will introduce you to our villain, our parasitic villain. This is Passeromyia longicornis. And it is the larvae of this species. So yeah, this parasite is the larval stage of a fly that is very closely related to your ordinary everyday housefly. But this fly parasitizes young birds, and it does that by boring into the exposed skin of baby birds, and then once it's in there, it feasts on their bloods, on their blood, and then the maggots get really fat, and the baby birds eventually end up dying.
Oh, that sounds really unpleasant.
It sounds very unpleasant.
Such smart and cute little birds.
I know. And it's not just affecting a couple of these 40-spotted pardalotes. It's having truly decimating effects on the species. So it's killing up to 9 out of 10 pardalotes in some of the areas. So that's that's a huge decimation of the population of a population that's already at risk. And you know, if the species was healthy and numbers were larger and stronger, then the parasite wouldn't be so much of an issue. Parasites are part of the ecosystem. You know, we don't want to remove them. But because the numbers are so low and the population so fragmented, this fly larvae parasite's now threatening the entire survival of this species. So now enter, stage left, researchers from the Difficult Birds Research Group from the Australian National University.
Difficult Birds Research Group.
Yes, the Difficult Birds Research Group. If you haven't heard of the Difficult Birds Research Group, you should definitely look them up online. They are fantastic.
way to victim blame the birds there, I think.
Or is the research group difficult? Is it the...
No, it's the birds.
Okay.
They're difficult birds. Like, not difficult in the way that they act with each other, I imagine, but more difficult as in the problems that face them are difficult, Okay, so our researchers Fernanda Alves and Dejan Stojanovic are working out the best and most effective way to help protect the 40-spotted pardalote from attack by the maggot parasites. And incredibly, they have figured out a way, and it's very clever. It involved, first of all, understanding that the pardalotes love to make soft, warm nests, as a lot of birds do. But these nests aligned with stray feathers of other birds that they find on the forest floor. And, I mean, I don't spend all my time looking for feathers on the forest floor like a pardalote who's making their nest would, but you don't often find that many, lovely feathers that would work well to line your nest. So the pardalotes have quite a hard time, it's time consuming and it's difficult work to try and find all these feathers. Yes.
I don't know much about 40-spotted pardalotes, but I'm familiar with like some other spotted pardalotes that we see around in Melbourne here. And I know that their nests are in burrows in the ground. Are these 40-spotted pardalotes also burrowing birds?
No, these birds nest in trees.
Okay.
Yeah. So they nest in trees and they nest in, have these like extremely warm, like feather-lined nests. Okay. And so the researchers have decided to exploit the fact that the feathers are in short supply and bring in their own supply of feathers, special feathers, chicken feathers. Not just chicken feathers, but sterilized chicken feathers that are laced with a bird-safe insecticide that stops the parasitic fly developing in their nest. So, the researchers went about, I guess you would say, MacGyvering or crafting a chicken feather sort of shop front that was made from scrap wire, some duct tape, and some of those round plastic trays that you get at the bottom of pot plants. And they've created what's effectively a sort of self-service feather dispenser, putting them in forests where the 40-spotted pardalotes were building their nests. And according to the researchers, it didn't take long before the pardalotes found these free and easily accessible building materials. In fact, their conversation article, which you can read online, includes the hilarious quote, "Our dispensers were as busy as the toilet paper aisle during a pandemic." Lol, researchers. I love it. And when they went back to check, some of the birds' nests were at least partially, and some of them were almost mostly made from the medicated feathers.
So I assume that basically, so the idea is to provide them with a supply of parasite-free feathers, rather than the parasite-ridden kind of wormy ones that would have got off the forest floor.
Well, not just parasite-free, but ones that have insecticide in them. So they are going to, kill any potential parasites that could be in any of the other ones. Yeah. So I'm sure you're wondering how the results went. Whether more pardalotes survived because of the pesticide-treated chicken feathers. Well, yes, they did. Survival of chicks dramatically improved in the nests built with the insecticide-treated feathers, and on average, 95% of chicks from these birds that use the treated chicken feathers survived, compared with 8% of the birds that used feathers without insecticide. So that's a huge amazing jump. Yeah. So this is more than, I guess, a 10-fold increase in nest survival. And for anyone out there feeling sorry for the parasites, and that's fair enough, Everyone's got to make their way in the world. Never fear, there are other birds who also fall victim to these parasites, so it's not like this fly will be driven to extinction. But what has happened, though, is that the researchers, through understanding their birdie behaviours, have managed to create this clever, cheap and wonderfully effective innovation.
We all probably had to do chemistry of some description at school, and it's so full of rules, but it does seem to be a pretty simple combination of maths dictating the way various substances interact in predictable ways. That's my takeaway from chemistry from when I had to study it.
Right. I mean, I'm sure you've made a lot of Year 12 students around the country feel much more confident about their upcoming chemistry exams. Guys, it's just maths and how maths dictate, the movement of atoms.
Hey, look, as far as it goes, you can be right or you can be not right in chemistry. That's kind of how it rolls.
Yeah.
So we have all the atoms on the periodic table representing all the known elements and a couple of predicted ones that haven't been seen, but they're likely to exist. And we know that when combined in certain ways, those atoms form molecules in, again, pretty predictable ways that have been demonstrated repeatedly with experiments to show how they consistently make those molecules. And we also know that matter, like atoms and molecules, behave in certain ways according to conditions in their environment. And there are various phases of matter. Claire, do you know what the phases of matter are?
Oh, you mean like gas, liquid, and solid?
Yeah, and...
Oh, and plasma.
And plasma.
Yeah.
Exactly. So we've got liquids, gases, solids, our most commonly encountered phase of matter, and we have a pretty good understanding of them and how they behave. If you superheat a substance, it can create another phase of matter called plasma, which has its own properties again, and only occurs under very specific circumstances, under immense heat and pressure, like, in a star or somewhere like that, is probably where we would most likely be able to find plasma.
You're not going to find plasma in your kitchen.
No, probably not.
Right. Okay.
No. Although, if you built the right machines, you could probably make some. I don't recommend it. It's not safe.
Great.
For home use.
Fantastic.
Now, if we take something simple like water and put it under very extreme conditions, say extreme heat and pressure, what would we expect to happen?
Extreme heat, extreme pressure. You'd think it would, I guess, vaporize, turn into a gas, right? Water vapor.
You would think that. You would think it would turn into a gas or maybe even plasma if the pressure and heat was enough. But if we took water and did that to it, we would not get that. As some scientists from the Lawrence Livermore National Laboratory in California showed last year, they put a droplet of water under very extreme heat and pressure using super powerful lasers. And, well, they weren't exactly surprised to find it formed a new kind of solid, which is basically hot black ice.
What?
So they've turned water into a substance which is solid, and it's hot and it's black, but it's made of water.
Hang on. Is that... Whoa, what? Have they just burnt the water?
No, the water's still there.
But it's black.
It's black and it's hot.
It's hot.
Yeah. Ice and water have a very simple chemical formula. It's 2 hydrogen atoms and one oxygen atom, H2O. And ice crystals can form in up to 17 different crystalline patterns depending on the conditions that they're in. There are 12 distinct types of ice crystals already recorded, but they are mostly cold and they're more or less transparent, which is like the ice cubes you get out of the freezer. This new black hot ice is solid, but it's 4 times heavier than normal ice and really quite hot. It has a melting point of around 4,700 degrees Celsius.
Why is it so heavy?
Because it's condensed. It's like been pushed into this shape by the extreme heat and pressure.
So it's a lot denser.
Yeah. And it conducts electricity like a metal.
Whoa!
Yeah. So it's really weird stuff that they've discovered.
What are they calling it?
Well, it's called superionic ice.
Oh, yeah.
Yeah, because it's superionic.
Yeah.
But probably the most amazing thing about this discovery is that it answers a lot of questions about some of the giant planets in our solar system, like Neptune and Uranus. They are frozen. They're not gas giants like Saturn and Jupiter. They are frozen planets. But they could never work out what made them up, because they're too small for it to be made of regular ice. So what was actually making up the core of these planets? And now they actually think that it's this superionic black ice that is making up the bulk of these planets. So possibly, so these gigantic planets have weird magnetic poles, and the presence in their makeup of this new superionic black ice could explain why those magnetic poles are so hard to pin down, because they're being affected by the electrical conductivity of the superionic ice that's forming these planets. So the crystalline structure is quite different. The water molecules separate into oxygen, which forms a kind of cube, sort of like a lattice of boxes all joined together, and the hydrogen moves around inside this framework of oxygen cubes. So it's a completely different kind of water than we've ever seen before.
And is that common in solid structures, that you would have hydrogen atoms moving throughout? It seems, yeah.
It's really unusual and it hasn't been seen before, but this research tends to suggest that this might be the most common form of water in the universe.
Hang on, what?
Yeah, so all of the H2O, most of it is in this form of hot black ice and not in the form of frozen water as we know it at all. So it's pretty amazing. But what these guys are thinking is that they can possibly get into a new era or a new area of research in materials physics. The data that they collected doing this to this droplet of water matched exactly their predictions about how it was going to behave. So what they're thinking is that they can predict the way other things will behave when put under certain conditions. And what they're saying is that in the future, we may be able to create new materials with whatever properties they like.
Wow.
So they can build a substance to order based on what you want it to do, which is a pretty huge leap forward in sort of materials technology. So it's a pretty amazing discovery, and I'm still sort of amazed that this didn't get more attention when this happened last year. It just goes to show that even in a field as well understood as chemistry, with a substance as common as water, there is still new science to discover.
Across Australia on the Community Radio Network, you're listening to Lost in Science.
Tears of wine have been... It's a phenomenon with a good vintage. It's been known about for centuries.
Now, what is it, though?
In fact,
Chris, can you clearly explain what you're talking about here?
Okay, so what happens is when certain wines, they will form around the glass above the liquid. There will be some small drops formed. It's kind of a ring of, you see a thin ring of liquid, and that drops like tears come down from it.
So you can sort of see lines. They're almost like translucent lines that are coming down from the uppermost part of where the liquid was.
Yeah, something like that. Now, as I said, look, this has been known about for centuries. There was actually allegedly a line in the Bible that mentions it. It talks about the wine moving by itself. It says, "Look not thou upon the wine when it is red, when it giveth his colour in the cup, when it moveth itself all right." So that's some people saying, oh, it's because the wine is moving. That's the tears. But that line is also useful because it's kind of a clue to what's going on with the wine. Because you're experts, you're people in the trade, like Claire, who know the legs of wine, often think, oh, this is a sign that the wine is really good.
That's what I've heard, people in the biz tell me.
But really, all it means is that there is high alcohol content.
Oh, doesn't that mean good, Chris?
Well, okay, that could be construed as good. It could also be explained why it gives you tears as well.
Yes.
There's a lot of depth to this. There's a lot going on here. But look, the basic phenomenon is known as the Marangoni effect. It's named after the Italian physicist Carlo Marangoni, who actually did his doctoral thesis on this topic way back in 1865.
Wow.
Yeah.
That was a while ago.
That was...
Just as an aside, could you find his published work online?
I haven't looked it up. I don't speak Italian. I don't read Italian. I don't read 19th century Italian, I'm sure.
Oh, he didn't translate it?
Into modern English? I don't think so.
Ah.
But look, what it means, what the Marangoni effect is, when you have two regions in a fluid with different surface tension, then the liquid will flow from the lower surface tension to the higher surface tension. Because the higher surface tension is kind of pulling on it more.
So it's kind of like a potential thing.
Yeah, it forms a sort of a potential. Like this effect can be seen in lots of places. It is actually used in manufacturing. It can be seen apparently in soap films or surfactant films, like a detergent, like soap forms of film. What happens there is if the film thins out for some reason, then that reduces the surface tension in that part, and so it increases surface tension in that part, and so the fluid will go and fill up the thinning out bit. So it makes the film stable by, it evens out the areas of surface tension. So it's a nice little effect that it has kind of in a practical sense, but also works well with wine because alcohol has a lower surface tension than water. So what happens, I've got an empty wine glass here. But
you do. I can verify that.
I'm going to be using this later on. But when you have, say, when you have a liquid in a container and it forms a meniscus where it kind of climbs up the edge of the glass.
Yes.
Yes. So that bit where it climbs up the edge of the glass, that is thinner than the rest of it. And so the alcohol in that section will evaporate more than in the main part. Mm-hmm. And alcohol has a lower surface tension than water. So what this means is there is more water around the edge than there is in the middle. And so it will move towards the area of higher surface tension, which is around the edge. And this causes it effectively to climb up the sides of the glass. You got that?
Yeah.
Yeah.
But then the question remained, why does it form these tears? Now, this is basically the subject of the paper that was published in March in the journal Physical Review Fluids, a team from the University of California, Los Angeles. They did a lot of maths, a lot of partial differential equations, and they did some experiments. They used different kinds of glasses, like conical glasses they found were really effective, like a martini glass kind of thing. And they used port wine because that was a fairly high alcohol content. And they found that...
I hope they used, they didn't use conical flasks, just conical glasses.
Well, a conical flask goes around the wrong way, doesn't it?
I know, but also never drink out of your labware, am I right?
Yeah, it's a bad practice.
Well, you clean it, don't you?
It's a bad practice. I don't expect physicists to understand, but it is a bad practice.
Yeah, we don't deal with that kind of stuff.
No.
We'll drink out of anything, basically. Yes. So what they found happens is that, and we're gonna try and repeat this in a bit, because they said they gave instructions for how to repeat this phenomenon at the dinner table, is the way they put it. Basically the wine travels up the glass in a wave. It's specifically what they call a reverse undercompressive shock wave.
Undercompressive.
Undercompressive. So
It sounds a bit underimpressive.
a compressive wave basically is when you have the stuff in, you have a wavefront, the stuff in the bulk of the wave, behind the wavefront, is moving faster than the stuff in front. And so that's kind of pushing forward like that. Right?
Right, yep.
And undercompressive, in this situation, but essentially the stuff behind the wavefront is moving slower than the wavefront. And so it kind of thins out. So you actually get this, that's why you get this kind of band moving up the glass, because it's thinning out behind the wavefront.
Right. They're waves you don't want to surf at the beach, right?
No, that would probably, do you some damage, I reckon. Yeah, you would kind of end up dumped into the sand or something like that. So one of the characteristics of a reverse undercompressive shockwave, as you probably realise, is that if any perturbations or imperfections will go through the wave instead of being carried along with it. So these imperfections become the tears that then drip down from the wavefront. Okay,
Right.
so we're going to try and repeat this. I hope you've got your wine
at the ready.
I am going to actually... I'm actually
At the
going to
ready.
use... Good, thank you. Claire, I can see you've got a nice glass there.
Nice glass of red.
Yep.
It's Shiraz.
I'm actually going to use some brandy, because this has like 37% alcohol. If this doesn't work, nothing will. Now, so the instructions, I didn't give you instructions before we started this, so I can see you've already broken it. They say to pour a bit of the wine into the glass and then put a lid on it. The reason you put the lid on it is, and this may not be a problem for you, Claire, is to stop it evaporating too much, because what you do, first of all, you try to have to wet the glass. So you swirl it around so that the glass is actually wet, because the wave works better when it's wet than when it's dry.
Swirling. Yep.
And then you let it sit for a bit.
Okay. Sitting.
Okay.
It is
for a
now
few
sitting.
seconds. Now, I can't say this is always going to 100% work, but we're going to try it. And then the idea is if you take the lid off, or at least in my situation, then what you'll find is that you will have, the evaporation will start and you'll get your tears. Now, with my sherry, I'm going to hold that up to the camera. I don't know if you guys can see that. No, you.
Oh yeah, a little. Yeah.
You can see the tears running down from a ridge, like a circle that's around the top of the wine.
Yes.
Yeah, like a high watermark almost.
You see all this, yeah. Yeah, it's a high watermark.
Yeah.
How's yours going, Claire?
Yep. I've got some tears and a high watermark.
Excellent. And what alcohol concentration do you know on your wine?
15.
15. That should be good enough, yeah. Excellent. Stu, did you get anything there going on with yours?
Yeah, a little bit, but I think mine's only about 12%.
Like I said, this is kind of used by people to say, measure the quality of wine, allegedly. Essentially, it's measuring, like I said, just the alcohol content. If you think that's a good quality wine, is high alcohol, then good on you. If that's what you're looking for, it is a way to test the alcohol content. But essentially, it's something you can try at home if you're home bored and all you've got is wine. Well, you probably don't have much of a problem, but here's something you can do with it just in case.
That's all we've got time for this week, and we are rapidly running out of time. If you want to get in touch with us, you can email us. You can find us on Twitter and Facebook. We are broadcast across Australia on the Community Radio Network with the financial assistance of the Community Broadcasting Foundation. And if you would like to tune in next week, Chris, Stu, and Claire will get
Locked in
Science!
Thanks for listening to a 3CR podcast. 3CR is an independent community radio station based in Melbourne, Australia. We need your financial support to keep going. Go to www.3cr.org.au for more information and to donate online.